Early in 1945, not far from Japan's shores, an American F4U Corsair had to ditch in the ocean after its engine failed during a combat mission. The pilot bailed out as the fighter hit the cold Pacific, and within hours, Japanese patrol boats reached the floating wreck. What they pulled from the water turned into one of the biggest intelligence chances of the war's last months. For almost 3 years, Japanese pilots had battled this American fighter over the Solomon Islands, Rabaul, the Philippines, and finally the home islands. They knew it was fast, heavily armed, and amazingly tough, but they had never recovered a full, mostly intact Corsair they could inspect, measure, test, and truly understand. Japan's encounter with the F4U Corsair was more than a story of a captured airplane. It became a moment of technological awakening when engineers faced the scale of American industrial strength and advanced engineering. By studying the fighter closely, they discovered hard truths about production precision, materials, and design choices that challenged their own assumptions and showed exactly how far behind they had fallen. The Corsair they recovered embodied the peak of American fighter development. Designed in 1938 to meet demanding U.S. Navy goals, it grew from a bold idea into one of the war's most feared aircraft. Its inverted gull wing, huge Pratt & Whitney R, 2800 double Wasp engine, and standout performance made it instantly recognizable. More importantly, it achieved a balance that Japanese aviation struggled to match: high speed, heavy firepower, long range, and strong structure. The story began when the Navy asked for a fighter that could top 400 miles per hour in level flight, an ambitious target when most fighters struggled with 350 miles per hour. The Navy wanted everything at once: speed, low stall speed for carrier landings, 1,000 miles of range, heavy guns, and the ability to carry bombs. Chance Vaught's team, led by chief designer Rex Beisel, chose to build around the largest, most powerful engine available, the 18-cylinder, two-row R2800, producing about 2,000 horsepower, nearly double many rivals. To use all that power, they fitted a massive 13-foot 4-inch propeller, the biggest on a fighter at the time, which created a challenge: how to keep the propeller clear of the deck with landing gear short and strong enough for carriers. The answer became the Corsair's signature: the inverted gull wing, with the wing bending down from the fuselage, then flattening out, allowing shorter gear, solid prop clearance, and smoother aerodynamics. The prototype XF4U-1 first flew on May 29, 1940, and later, on October 1, 1940, it hit a ground speed of 405 miles per hour with a tailwind, the first U.S. single-engine fighter to reach that mark, while true max level speed was about 378 miles per hour at 23,500 feet. Still superb for 1940. Production F4. U-1s reached units in late 1942, with Marine Fighter Squadron VMF-124 receiving the first combat-ready planes and deploying to Henderson Field, Guadalcanal, on February 12, 1943. The Corsair's combat debut was rough. On February 14, 1943, in the St. Valentine's Day massacre over Bougainville, U.S. forces lost 9 aircraft, including 2 Corsairs, plus P-38s, P-40S, and bombers, while the Japanese reportedly lost only 1-0. The lopsided result forced a rethink of daylight bombing tactics. This showed that advanced technology alone did not guarantee success. Tactics, training, and deployment mattered as much. Pilots soon adapted, learning that the Corsair was best used with boom and zoom tactics. Stay fast and high, dive to attack, fire, and climb away before the enemy could turn and counter. The Corsair could not outturn a Zero in a slow fight, but it could outdive, outclimb, and outrun any Japanese fighter. Using these tactics, Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, ultimately scoring 21 victories. Through 1943 and 1944, the Corsair's reputation grew. Marine squadrons flying from rough coral strips in the Solomons leaned on its ruggedness. The aircraft took damage that would have brought down lighter opponents. Its 6.5 zero-caliber Browning machine guns, with a total of 2,350 rounds, delivered fierce firepower. Some later variants replaced the 6.50s with 420mm cannons, though many pilots preferred the reliability and ammunition volume of the .50 caliber setup. The Corsair's role widened too. By mid-1944, it regularly carried bombs, rockets, and napalm canisters, making it a valuable fighter bomber for amphibious operations. During Okinawa in 1945, Corsairs flew thousands of ground attack missions, earning the name Angels of Okinawa from grateful troops. What Japanese pilots saw in combat was only part of the picture. From a cockpit, a Corsair looked faster, stronger, and tougher. But to understand how it was built and why it was so effective, Japanese experts needed to examine a real, mostly intact aircraft. Japan's top facilities for this work were the Yokosuka Naval Air Technical Arsenal near Tokyo and the Army Aviation Technical Research Institute at Tachikawa. They had studied captured Allied planes throughout the war, but most were damaged wrecks. An intact frontline American fighter was a rare chance. Yokosuka had been doing high-level technical research since 1932 and employed thousands of engineers and technicians, designing many Navy aircraft, even if companies like Aichi, Nakajima, and Mitsubishi built them. When the salvaged Corsair arrived in early 1945, it was one of the most modern American fighters they had recovered in decent condition. Water had damaged it, but the airframe remained sound. Crews had kept it from sinking, and it was hauled into a secure area for study. The first step was to assess damage and document measurements. Despite the saltwater, much was intact. The big engine needed a full teardown and cleaning, but the structure showed no combat damage, which mattered because earlier captures made it hard to tell design features from battle damage. Specialists photographed everything and recorded dimensions: 40 feet 11.7 inches of wingspan, 33 feet 4 inches in length, and about 15 feet in height with wings out, or over 16 feet when folded for carrier storage. The inverted gull wing stood out. Japanese designers saw its aerodynamic and structural benefits, but also its manufacturing difficulty. Making those compound curves and tight angles at scale required advanced tooling and quality control many Japanese factories could not maintain in 1945. One surprise was the use of fabric on parts of the outer wing surfaces and control surfaces. By 1944 to 1945, most modern fighters were all metal. But deeper studies showed this was a smart, early design choice from the 1938 to 1940 period. Fabric saved weight where loads were low and conserved aluminum for high-stress parts. Properly treated fabric could be strong and weather-resistant while being much lighter than metal skin, reflecting a mature, resource-savvy approach. Taking the wing apart revealed methods that impressed and worried the examiners. The main wing spar, a single, large, critical beam, was a high-quality forging. American industry could produce big, complex aluminum alloy forgings with consistent strength, while Japanese factories increasingly relied on building up structures from smaller pieces, which was easier to make but not as strong or consistent. The internal ribs stamped from sheet aluminum were also highly consistent, each piece matching the next with tight tolerances, showing strong process control. By contrast, late-war Japanese production often struggled with consistency as materials and skilled labor became scarce and air raids disrupted factories. The Corsair's armament installation told the same story. The 6 wing-mounted .50 caliber Brownings were not only powerful, the entire setup, ammo boxes, feeds, ejection paths, and charging mechanisms, was integrated and easy to maintain. The machine guns themselves reflected top-tier precision manufacturing. Decades of refinement and massive production made Brownings reliable and uniform in a way Japanese industry struggled to match. Armor protection was another lesson. The Corsair had about 150 pounds of armor around the cockpit and thick bullet-resistant glass behind the windscreen. Japanese fighters had largely sacrificed armor to keep weight low for better maneuverability, a trade-off that had worked early in the war. But as American fighters grew stronger and more heavily armed, the lack of protection became deadly. The Corsair showed that with enough engine power, designers could include significant armor without losing performance, and the R2-800 provided that power. The engine dominated the technical review. The Pratt & Whitney R2800 double Wasp was a high point of American piston engine design. 18 cylinders in 2 rows, 2,800 cubic inches of displacement, and more than 2,000 horsepower. Japanese engineers had seen it before, but not one this intact. Its construction revealed manufacturing capabilities that were hard to match. Precisely machined cylinders, finely finished pistons and rods, and a supercharger with complex passages and exact fits. Japan had struggled to develop similarly effective 2-stage superchargers because of manufacturing limits. Reliability also stood out. American radial engines often delivered rated power for hundreds of hours between overhauls. Japanese engines often fell short of theoretical power and needed frequent maintenance. The R2800's consistency came from better metals, better lubricants, tighter tolerances, and stronger quality control. The giant Hamilton Standard propeller, with its variable pitch and hydraulic control, showed advanced aerodynamic and manufacturing skill that Japan found difficult to replicate at the same size and precision. Across the aircraft, the same pattern appeared. The landing gear was complex, yet precisely made. The cockpit had a full set of instruments and controls beyond anything in Japanese fighters. The fuel system used self-sealing tanks with layered rubber compounds that swelled when punctured to limit leaks. Technology Japan mostly lacked. The electrical system was robust and neatly wired with good insulation. Most of all, materials and workmanship were consistently high from major parts to tiny fasteners. Aluminum alloys behaved predictably. Steels were correctly heat-treated. Surface finishes were smooth. The airplane felt solid and built to last. By contrast, late-war Japanese production suffered from shortages, substitute materials, loss of skilled labor, and constant bombing, all of which hurt quality. The captured Corsair arrived as Japan was nearing defeat. B-29s were burning cities. The fleet had been shattered at Leyte Gulf. The Philippines were lost. Iwo Jima had fallen, and Okinawa was under attack. In this context, the Corsair inspection felt less like preparing for future wins and more like a sobering assessment of reality. Engineers at Yokosuka and Tachikawa wrote careful reports of their findings, listing measurements, describing production methods, and judging American capabilities. Their tone was professional, but the implication was clear. In almost every area, American technology outpaced Japan's, and the gap was wide and not quick to close. It was the product of years of industrial growth, big investment in research and tooling, mature supply chains, and resources Japan did not have. By August 1945, at least 2 Corsairs had been captured. Evidence suggests technicians tried to repair at least one toward flying condition, as photos show patched wings and fuselage, though it is unclear if it ever flew. When American occupation forces entered Yokosuka in September 1945, they found captured Allied aircraft, stacks of technical notes, drawings, and photos, proof of Japan's sustained effort to understand Allied technology. U.S. intelligence collected these materials to learn what Japan had learned. The examination of the F4U Corsair came to symbolize the large gap between American and Japanese aviation by war's end. In early 1943, skilled Japanese pilots in Zeros could still fight well using better tactics. By 1945, even experienced pilots in newer Japanese fighters struggled against well-flown Corsairs. The Corsair's technical edge, combined with American numbers and improved training, created overwhelming odds. Officially, Corsairs claimed about an 11-to-1 kill ratio against Japanese aircraft, with 2,140 Japanese planes shot down for the loss of 189 Corsairs to enemy action. Those numbers reflected not only the Corsair's design, but also America's training, logistics, production scale, and technology across the board. Japanese engineers reading the data could see the performance gap, the manufacturing differences, and the resource imbalance, and their reports amounted to a frank admission that Japan could not match American industrial strength. The Corsair's story did not end in 1945. It served long after World War II, proving itself in Korea from 1950 to 1953 as an effective ground attack aircraft, even as jets took the air to air lead. Several foreign air forces, including France, flew Corsairs in conflicts into the 1960s. The last combat missions occurred in July 1969 during the brief Soccer War between Honduras and El Salvador. On July 17, 1969, a Honduran pilot flying an F4U shot down 3 Salvadoran planes, including 2 FG-1D Corsairs. An ironic end, as its final victories were against the same type. From its first flight in 1940 to its last combat almost 30 years later, the Corsair proved to be one of history's most successful and long-lived fighter designs. For Japan, the Corsair encounter was part of a broader post-war reckoning. Engineers who had struggled with shortages and limits during the war now worked with American authorities to rebuild industry. Lessons from studying American technology, including the Corsair, shaped Japan's post-war approach to manufacturing, with an emphasis on quality, precision, and continuous improvement. The aircraft recovered in early 1945 became more than wreckage. It was proof of engineering excellence and disciplined production that Japanese aviation had sought during the war. The lessons came too late to change the outcome, but they influenced the peace that followed. In examining the Corsair, Japanese engineers had to face the full scale of the challenge. Bravery and skill alone could not overcome an opponent with massive technological and industrial advantages. The story ends not in triumph, but in acknowledgement. The technical reports gathered by the Allies and preserved in archives stand as quiet testimony to a moment when one nation's engineers confronted another's capabilities. The captured Corsair itself is gone, likely scrapped amid post-war chaos, but its legacy remains in the clear lessons it taught about what is possible when technology, resources, and manufacturing discipline are aligned. Japan's aviation sector would rise again, but its engineers would not underestimate American potential in the face of powerful industry and science. The 1945 examination of the F4U Corsair marked a true turning point. A lesson written not in speeches or battle claims, but in aluminum, forgings, tolerances, and production mastery that revealed the real shape of American industrial power.